Hey everyone, so continuing on with the chemical potential equations, we're going to continue doing a few more questions. So this question is piggybacking off of the previous equation that we had before, where we had the concentration as a function of the magnetic field. So pause the video, work on this stuff, and we'll go over it in a second. All right, so as you recall, we had two equations for the concentration as a function of the magnetic field. We had this one that had the e's involved, and then we had the cosine one. Now, this is what I said before about how it becomes significantly easier to solve for certain things using this form of the trig function. So this is what we're actually going to end up using because they want the ratio of m over tau, which would be fairly hard to actually derive and analyze from the first form of the equation. In this form, it's a lot easier. We're looking for this ratio, so we just divide the n0 over and do inverse cosine of both sides, just like we would if we were trying to find the angle based off of um, length, width, and hypotenuse of a right triangle. So from here, we have this equation for the ratio, and we just have to plug the numbers in. So they give us everything up here, plug and chug, and you should get 2.65 inverse Teslas. All right. For part B, they want to know how many Bohr magnetons this would be in order to get this concentration effect. So what we're going to do is we're going to take the value of m and divide it by the mu b. Now, one of the things, this mu, I want to actually point out, this mu is not the same as the chemical potential mu. Right? Um, so here, what we're going to do is we're going to start off with our ratio, and we can see that we can get this ratio by essentially multiplying this by tau over tau and then distributing one of the taus to each of these terms. So we end up having something that looks like this. So we already know what m over tau is, and we know what this tau can be broken up into. So from there, it's just plug and chug the numbers that we have and get that pretty much it would be equivalent to a little bit under 1200 elementary magnets, essentially electrons. Smallest possible magnets that we could have. All right, here's the next question. Pause the video, work on the self, and we'll go over it in a second. All right. So from here, they want us to find the concentration as a function of radial distance from the center, and we have something that's spinning around. So we're going to have to come up with an equation for this. Now, the way we're going to do this is using the concept that energy or work is the integral of work as a function of, of force as a function of distance. Moving around in a circle, that force is going to be the centripetal force, and the distance is going to be the radial distance. So that's where this is coming from. The fact that work is the integral of force with respect to distance. So plugging in an equation for the centripetal force, it's m omega squared r dr. So from here, all we have to do is integrate r as a function of dr, and it just turns into half r squared. And from there, combine into pretty much do the same thing that we did last time. Of course, if you want to incorporate the shortcut, you could do it here. But again, the way we do it is by setting the total potential at some distance r equal to the base concentration potential. So moving things around, I know it's really hard to see, but this is supposed to say n0 e to the m omega squared r squared over 2 tau. All right, here's the next question. Pause video, work on itself, and we'll go over in a second. All right, so here, there once again we have water being raised in a tree, and we're trying to figure out what the concentration is as a function um, of the vapor in the air based off of these values. So what we have here, what we can do is basically that equilibrium equation that we had before about how the change in the internal is equal to the change in the external. So the internal chemical potential, just the difference in the concentration equations. So we have N0 for at the very bottom, and it says at the very top it's going to be Rn0. So I just replace that in. And then I can combine these, and you can already see that a lot of these drop out, and it ends up simplifying as just tau ln of r. The external is going to be equal to the negative of this, and we already know that the external is going to be the gravitational potential because we have the water being raised to some height. So solving this and solving for h, we end up getting this. And then from here, it's just plugging in the numbers that were provided to us to find that the max height is a little bit under 1,500 meters. This is actually one of the reasons why there is a pretty much a limit to how tall trees can get. All right, so moving on, we can actually take the equation that we have for the chemical potential and relate it to the entropy. So as we know, that entropy is given by this more extended equation. So we had before, I believe we looked at these two parts, that the entropy was just could be brought in as a function of, or a sum of the partial derivative of the entropy with respect to u, partial with respect to v. Now we can actually include partial with respect to n. So from here, what we're going to say is dv is going to be 0, and d tau is also going to end up being 0. So this whole part is going to drop out because we're pretty much assuming that the volume of our system isn't going to be changing. The only thing that's going to change is how much energy is transferred, and from heat and the number of molecules. So this ends up looking like this, or simplifying to this. I can actually divide a delta n through each of these terms so that I could have the change in the entropy divided by change in n, so on and so on, and then it ends up crossing out this delta n over here. From here, we can actually combine this into one complete term as a function of tau v. And then we end up having, again, these all kind of being combined together. Remember, this is also, we have to include when we divide it over, we have to include the volume being constant because that's what's going on. We can actually simplify this change in the entropy term as 1 over tau. And now we have this. I know it's a little hard to see. I apologize. Now we can actually multiply the whole thing by tau so that we get over that 1 over tau part. So this ends up being our simplified entropy equation. Now we know that chemical potential is being defined as this, the partial derivative of the free energy with respect to the number of molecules. Now, if you remember, free energy is a function is equal to the internal energy minus the heat added to the system. So this partial derivative with respect to n can be distributed between those two terms to get us this. Comparing and looking at these equations, we can already see that we have the du dn up here. We also see that we have the tau d sigma over dn right here. So all we have to do is just move things around so that we get one side looking like this, and then set that equal to mu to figure out what the other side's going to be equal to. And that's what we have right here. We can move this over, take the negative of it, and this is what's going to remain. And we end up seeing that negative mu is equal to this. Or another way of saying it is that the chemical potential is negative tau d sigma over dn. Again, just coming up with a nice web of equations to work with. So this is a nice little summary of all the different equations that we've come up with so far relating temperature, pressure, and chemical potential to the variables of entropy, internal energy, and the free energy. All right? So depending on whichever one we have and whichever one we're looking for, we have ways of going around through them. So this is, like I said, one of the main things that we're trying to come up with is this web of equations. The only one that doesn't seem to be involved is this one. It seems that there is no equation relating the free energy to get to the tau. All right, so here's a question. You can pause the video, work on it yourself, and we'll go over in a second. All right, so going back to the whole Einstein solid, you'll see this a few times. Like I said, one of the things that I try to do is I'll show you the how the equations get derived, and then the goal is for you to try to repeat that process with a different starting point. So we could do the same thing here, and this is my way of showing of how could you do it from a starting point or from a different starting point. So we're gonna do the Einstein solid, and for part A, what they want is us to come up with this equation for mu. Now, again, we have these equations. We have multiple ways of getting to mu. We can come up with a free energy equation, a concentration equation. But those two don't seem to really work out that well, since the only way to get to the free energy equation requires a partition function. But we do have this. Now, if I think about it, I need to find a way to go from the multiplicity function to this. Now, I actually know of one variable that is a nice bridge between these two terms, and that is entropy. I know a way to go from the multiplicity function to entropy, and I know a way to go from entropy to this. So that's what I'm going to end up doing. So I'm going to do this, the entropy being equal to ln of q, ln of g, plug this in and take the ln of it, and we get this whole mess. We know that mu is going to be related to that partial derivative of this entropy with respect to n. So all I have to do is take this and take the derivative of it. For this first part, the n's here, and then over here we're going to have to do a chain rule. So cleaning this up a bit, will end up getting me, once I move everything around very nicely and more very elegantly, leave me with this q plus n over n. Then what I could say is go back to my actual definition that this partial derivative times negative tau will be equal to mu. So we end up getting this, that mu equals negative tau ln of q plus n over n. Now, part B says how much the entropy increases when we add in a new particle. And we're going to assume these two things. N is much greater than Q, and N is much less than Q. All right. So first in the first part, we have N is much bigger than Q. Well, what this means is that Q over N is going to be a very small number, very smaller than one. So if I look at the ln function that I had before for this partial of the entropy, how much the entropy is going to end up changing by, we have this, the just actually pulling it through. So we end up getting Q over N plus 1. Now, because of N being much bigger than Q, we know that Q over N is a very small number. So this actually just simplifies to being equivalent to this, Q over N, being much less than 1. So this is essentially just 1, or delta sigma is approximately equal to 0. All right. So this is the first case for n much bigger than q. So the whole entropy change will be fairly small. Now in the second form, where n is smaller than q, what we end up having is this. Q over n is much bigger than 1. So when we get this, we get q over n plus 1. This 1 is barely even noticeable with the fact that q over n is a very big number. So this simplifies to actually just being ln of q over n. And once again, we know that this is going to be very small, very big. So we know that the change in the entropy is going to be very big. So what this is saying is that when we have a scenario where we add a new particle to the system, if the number of particles is much bigger than the available amount of energy, remember that's what this Q is representing. Q is representing essentially the amount, the quantum amount of energy, discrete amount of energy that the particles can have. So if the number of particles is very large compared to how much energy is available, adding in a new particle, it doesn't really affect it. It's barely going to change the entropy. But if we end up having a lot of energy that we can distribute between, to the fact where there's more energy than there are particles, adding in one extra particle will actually increase our entropy by a drastic amount. So that's what this equation ends up getting us. All right, here's the next question. Pause the video, work on this stuff, and we'll go over in a second. All right, so here we're going to end up coming up with equations for the partial pressure. Now, they tell us that the partial pressure is given as this. So as something that you probably should have learned in some of the previous physics classes and thermal classes was that when you have a gas mixture composed of all these different chemicals or elements, the total pressure is essentially the sum of all the individual pressures or partial pressures. So that's what this is pretty much saying here. All right, so they want us to come up with the chemical potential. So we know that the number of molecules is just going to be the sum of the two items, let's say. So we're basically just going to assume that there's two objects, the two species we have here, and sigma ends up being the sum of the two entropies. So the chemical potential is going to be set up like this. So again, the relationship between the entropy to the chemical potential. Bring it in for the two parts, we get that. So what we can actually say is that it ends up being something like this. So since we're doing the partial with respect to Na, this term actually ends up dropping out, and this is the only term with Na. So we end up having our chemical potential equation look something like this. So what we have here is basically saying this, that the chemical potential is going to be equal to the essentially the chemical potential of looking at the entire system, uh, but only as a function of Na, versus just imagining that it was only composed of that first species, if you will. So, as it says here, assuming that the gas wasn't even present. So that's pretty much what's going on here. This is looking at it as if the first gas is part of a bigger, of more things, while this is just looking at it as if we ignored that the other gases were present, and we're only treating it for the one gas. All right. So we can actually go back to some of our previous equations, and as we continue, we can actually further develop a lot of equations that we've gone before. So if you remember, we had this equation, which they call the thermodynamic identity, basically that the change in internal energy is equal to the work added to the system minus the work done on the system. Um, we can actually expand this a little bit. So going back to our entropy equation that we had before, uh, plugging in what we have for mu for all these things, like for example, this we already know is 1 over tau. This from our previous work is p over tau, and this is negative mu over tau. So we end up getting this. And then what we could do is just multiply tau across the board. And then move it around so we have du equal to everything else, and we end up getting this. So now we're adding a new type of term to this equation. So we're just building on this equation to include more types of energies. So the internal energy not only is taking into account the heat added to the system and the work done on the system, but is now going to take into account essentially the concentration potential energy of the system, which does kind of make sense that um, if you have a system that ends up having a higher concentration, it should end up having more internal energy going on that isn't something like increasing the work or increasing the heat. Like a good thing that one common thing I could think of is, if you have a gas that is in a fixed volume and you just keep shoving in particles, well, we know that increasing the concentration will end up changing the pressure and um, the temperature and all that. So that should also play a part towards the changing of the internal energy. All right. I guess I could start the Gibbs factor and then we'll continue on with some practice in the next part. Um, but the Gibbs factor is actually very similar to what we did with the Boltzmann factor. But now we're opening up our definition. So before, when we had the Boltzmann factor, you remember that came up with talking about how the probability changes uh, based off of two systems in thermal equilibrium. Well, now we have a situation where it's in diffuse thermal and diffuse contact. So now what we want to do is find a way to incorporate this chemical potential factor. So what we end up having is a total, we have these variables. We have tau being the temperature of the reservoir that's maintaining. We have the chemical potential of mu. We have the total energy, internal energy U0, and the total number of particles N0. So again, well, we kind of are going to do the same thing that we did last time. Like we said that the number of particles in the system is equal to N. So that means that the reservoir is going to be N0 minus N, so that we have it in terms of a constant and our only variable. Same thing here. We're going to define the energy of the system as epsilon, and that way we get um, the energy in the reservoir being the total energy minus epsilon. Um, all right, so sorry. So we know that the total number of states that can be found is just basically a multiplicity function of which the would be the product of the two systems. So again, the total multiplicity function of both is going to be the product. Since we're going to define one specific state for our system, that really just means that it's going to be the equal to the all the combination multiplicity states available to the reservoir. Once again, our probability is going to be proportional to this, which is going to be equal to this. And then if we take the ratio of the probability between two states, or our factor ends up looking something like this. So another way of writing all this is being just substituting as delta sigma. Mhm. Now, this entropy equation can actually be expanded a bit so that we kind of separate these equations so it looks something like this. And then we could take this one step further for the difference in the entropy. So we end up getting this whole part. So of state 1 and state 2. And you'll notice that there are some things that we can actually cross out and combine together to make it a little bit nicer. Now we can simplify these two terms as being minus mu over tau and 1 over tau. And once again, we can kind of move some things around, simplify it in order to get the probability ratio to look something that looks like this. Now, what ends up being important is this factor. The factor that we end up getting being n mu minus epsilon over tau. So this is what we're going to call the Gibbs factor. So it's literally just like the Boltzmann factor, except if you remember, the Boltzmann factor was just minus epsilon over tau. It did not include the concentration factor. So that's the difference between the Gibbs factor and the Boltzmann factor is this inclusion of concentration. Um, but it ends up being pretty much the same thing, that the probability of each state when taking into account the diffusive contact and thermal contact is going to be proportional to this. Once again, we can do the sum across all the states to get this. So this equation is called the Gibbs sum or the grand sum or the grand partition function. Once again, it works the exact same way as the partition function z that we had before. It's just now including in this chemical potential factor. All right. So most likely you're not going to be using this form. You're going to be looking at this form. We'll see exactly how this equation gets used in a bit. But it ends up working very similar to what we did with the regular partition function. If you remember with the partition function, a lot of the questions had systems where there was only like one or two possible states of energies, and so we were able to longhand answer it. We're going to end up doing the same thing here. There's going to be a few states, and we'll actually hand write out the sum in order to figure out an equation for the Gibbs sum. And just like last time, we could find the probability of it occurring at one state by taking the Gibbs factor and dividing it by the all this Gibbs sum. All right. And oh yeah, this is just saying that it's normalized so that when we sum across all the probabilities, we should get one. And that makes sense because when we sum across that, the sum goes towards that numerator, which is literally the Gibbs sum. So we end up getting Gibbs over Gibbs or 1. So, all right. So here's a practice question. You could pause the video, work on the self, and we'll go over in a second. All right. So here, they give us a setup. Um, they say that there's only one and only one electron that could be bound to the impurity atom, and it could either spin up or spin down. Then they also tell us that when there's no electron attached, the energy is 0, and when there is one attached, the energy is minus I. So they want to determine the probability of when the atoms are ionized and when they're neutral. All right, so first step, we want to come up with this Gibbs sum. Now, with the Gibbs sum, we end up having this. So we can either have no atom being ionized, no electron attached, and then an electron attached would spin up, and an electron attached spin down. So we end up having this. And then here, what they tell us is this, that we have the probability, as we know, is just going to be the Gibbs factor divided by the Gibbs sum that we already found. When it's ionized, then we already know that it's going to be basically 0 up top. So that can be simplified as 1 divided by this Gibbs sum that we found before. In the next part where it becomes neutral, an easy way of doing this is actually just saying that, well, if the probability of it being, it could either be ionized or neutral, that means that the probability for it to be neutral will just be 1 minus this original probability. So we can do that, and we end up getting this. So yeah, that's pretty much it. Or what you could have also done, if you wanted to, you could have kind of done it the same way, and again said, well, you have the two parts up top. So this part from the Gibbs factor stays, and then divide by the Gibbs sum. But either way, you end up getting this. All right. So we're gonna stop the video here. The next part should be a little bit shorter and focusing more on the practice questions. If you have any questions, let me know. Otherwise, I'll see you later.